Okay, cool, perfect. Thank you so much. Welcome again. I'm Bamburde. I'm a co-founder at Zyco Group, and I will be your host today. You can visit zycogroup.com to learn more about the company, but briefly, we are an R&D and consultancy consortium with interest in emerging deep tech and mathematics. Today, I'm pleased to have Dr. Jakob Kortman with us to talk about an open source project for designing variational quantum algorithm that he's been working on at Matter Lab in Toronto, more precisely as part of the Alain Aspuri-Gutzig group. Jakob's research focus has been on quantum algorithms for quantum chemistry and quantum optics. So I assume some of these, or most of the examples on the webinar will be mainly around these two topics, or at least one of them. The research software tooling landscape is really changing rapidly. For many years, fundamental researchers relied massively on commercial proprietary software, but over the past few years, seeing a seismic shift towards open source, where researchers are rolling up their sleeves and building tools that they need now. Tequila is an example of this trend, empowering researchers to unleash their creativity, knowing that they can test out ideas quickly from whiteboard sessions without going through too much technical hassle or waiting for a proprietary software vendor to build the tools for them. So today's session, we'll have like the main session with Jakob, and then we'll have the Q&As. On the Q&A, is enabled now. If you have a question, please do it on the Q&A instead of doing it on the chat. And please vote on the questions. This way it helps Jakob pick up the most relevant questions to try to reach out to answer to the wider audience as possible. And then we'll have, after the Q&As, we'll have like the close remarks. We agreed also with Jakob, there might be like a Q&A on the fly. So if during this presentation, there's something you don't understand, you can just type that actually on the chat, so I can just let Jakob know to see if he can address the question for you. Upcoming webinar, I'm pleased to let you know that Dr. Nicholas Chancellor from Durham University will be our next guest. We're still waiting for a concrete date yet. That's because he's meant to publish it at the end of this month or early next month. So the paper, the talk will be soon after the paper is published, which will make it very interesting for everyone. So it will be continuous time quantum computing beyond adiabatic. So it will be very interesting. I'm really keen to host Nick on this, and I hope you will join us on this talk. You can follow us on Twitter, Crowdcast. On Crowdcast, especially if you want to get notified for our other talks, not just with quantum computing, but also mathematics and a few other topics that we will be covering. So it's a good way to kind of connect with us. You can also search us on YouTube. Unfortunately, the URL is not that friendly. Apparently, we need to have like 100 subscribers in order for us to customize a URL. So for the time being on YouTube, you need to search us. So that's it. I'll stop sharing and hand over to Jakob. And thank you again for joining us. Jakob, just a moment. So I've stopped sharing. Jakob, the floor is yours.
Okay, great. Thanks for the introduction, Bambarde. Bambarde, sorry. And also thanks for the opportunity to speak here. I'm sharing my screen now. Give me 1 second. The window is gone. Okay, let me just reopen it.
Yes, someone is asking a question. This is for me. Yes, the answer is this webinar will be available on YouTube.
man.
Don't worry, Jakub.
Give me 1 second, like the browser froze. I guess I have to reload. I'm not sure if this will disconnect me.
Okay, no worries. If you disconnect, I can add you again. It's not a problem.
Okay.
Thank you, I really appreciate it. I actually wasn't aware of this, so you have to have 100 subscribers.
Okay, I'm back. Can you see my slides now?
Yes, I can see your slides.
Okay, great. Then this was just a small problem. Okay, great. Okay, then in that case, we can start. Yeah, I'm going to tell you a little bit about like open source software package, which is called Tequila, which we develop within the Aspero Gutzig group, and which is meant to be like an open source like development tool for new quantum algorithms. Like if you have like a new idea for a quantum algorithm, like which will help you like realize that idea like in a fast way, which is not too slow. But maybe let's dive into it like directly. Maybe in the beginning, like you see like the GitHub link below, you can go to the Aspero Gutzig group GitHub page, and there you will find the code. You can download it, fork it. You can make pull requests, like if you want to contribute something or raise issues if something doesn't work. So like feel free to play with it after the talk. So currently, like with quantum computers, like there's a lot of like investment and a lot of research going on, and people making like a lot of progress in it like nowadays, and like more and more people like are starting to think about how we can actually use those things to compute properties for problems which we're interested in, where one big field is like, for example, scientific simulation, which was one of the original ideas by Richard Feynman, like to build such machines. But there are also like other like examples, like for example in machine learning or even in finance, where people think about like doing optimization algorithms with those computers. And if you're thinking about like creating such an algorithm, like in principle, you can think about the quantum computer itself, if you want to, as a black box, like something where you send in some instructions and it gives you back some samples of expectation values, which means more or less like if you are able like to formulate like one of your problems you like to solve in the language of like operators, unitaries, and expectation values, you can more or less run it on a quantum computer. So like here in this comic, that's more or less like on the left-hand side, that's your idea, which you draw on a blackboard and say like, okay, I have like translated my problem into some Hamiltonian, and then like if I minimize the square of the expectation value of this Hamiltonian with some given wave function, then I can get an answer to some of the questions I had before. And in principle, you can use then the quantum computer more or less as an abstract black box machine, which gives you back the samples of those expectation values. You can, of course, also like not treat it as a black box and like take a look inside the box and see, for example, okay, like in order to run things like, for example, on a gate-based superconducting computer, you have to like translate your unitary operations into these elementary 1 and 2 qubit gates, how they are called, and think about like algorithms, how to like efficiently like partition some of those unitaries into those gates. So like go a little bit more into the technical details here. Or you maybe want to think about like how are like those operators actually measured, like how can you group them, how can you improve that? So there are different levels of how you can think about those things. And it really depends on what you're interested in top level algorithm design, or like first proof of principle results, or like very deep technical details, which like solve like very small problems and make them more efficient. here like a few examples of like people who thought about these things. Like on the left-hand side, this was like a so-called classifier. Like you have all these points which are inside the circle or outside the circle, and like they use the quantum circuit in order like to detect like if this point is in the circle or outside the circle. And they more or less then trained the parameters of this circle in order to have something like a quantum classifier. You could view this list like as a high-level algorithm design. Like if you can describe this unitary and then run it on the quantum computer, you can more or less like in the design of the algorithm, you can treat the quantum computer as a black box. Like in that work, actually, they went a little bit more into details and like did like the actual circuits, but like in principle, those are the two layers. In the middle, you have like, this is a very interesting work, like where people try to reduce the number of measurements you have to do for those expectation values by grouping the underlying Hamiltonians into commuting groups. And so if you have these commuting groups, this means more or less like you can measure them in parallel, or like you can do one measurement and evaluate every term of those commuting groups, which means like in the long run, you have like less measurements to do in order to sample your expectation values. They did it like with applications for chemistry, but like their algorithm works like in general. So like these are one of the things, like if you're interested yourself in such algorithms, it's like good to have those things implemented in an open source code, because then you can go look at the code, see in detail what it does, like learn in detail how it works, and then try to like extend it with your own ideas. And you're not necessarily have to start from scratch again. So like you can start exactly like where the previous work like stopped. On the other hand, like if you're like just interested in like high level design of those algorithms, and you want to run some small proof of principle experiments or simulations, techniques like these are also like super useful to you, because they decrease significantly like the amount of measurements you have to take, and they will make your initial tests much faster, and you probably can handle like larger systems as you could without them. So like if you have like a code base which can do this automatically for you, that's also like an advantage. So like, because otherwise you would need like to implement all of this from scratch again, and you probably, this was not what you intended to do like in the first place. On the right hand side, that's just like one of the first papers which use these type of like using the quantum computer as like a sampler of expectation values, and then having like a feedback loop. So like you have like a parameterized quantum circuit which gives you expectation values back, and those depend of course on the parameter then, and the idea was like to optimize those parameters like externally with classical algorithms. And this was like one of the first propositions here, also like with applications in chemistry. But nowadays, like you can use those things for a lot of like optimization problems. And the main task is like to transform your original problem into a language which has like these Hamiltonian circuits and expectation values. If we go back like to quantum chemistry, like classically, the development workflow, if you have like a new idea, looks more or less like this. Like you have some idea, like which is usually at the very high level. Like you say, okay, I have my electronic wave function looks like this. Maybe I can simplify it by, for example, neglecting some terms, or like minimizing a different quantity, like adding some penalty terms or whatever you might think about it. And then usually what you then have to do is like you have to derive so-called working equations, which means like you have to, starting from the high-level multi-electron wave function, like you have to decompose it down into sums of products of one particle wave functions, and then you have to contract them more or less manually, or like if you're lucky, there's some tools around which can do it for you. And this gives you like in the end like a set of equations which you can solve hopefully with linear algebra. And once you have that, you have to hope that you didn't make like any mistakes like in the derivation, and then you can do like a test implementation on this and see like if your original idea actually works and get some feedback on it. If you do the same thing for like quantum computation, like in a lot of cases, this tedious deriving of the working equations falls out, because like you can use your quantum computer more or less as a black box which samples your expectation values. It means more or less, if you have, in the conventional classical sense, one of those expectation values, you have to derive those equations to give this expectation value as an equation with respect to those one particle wave functions, for example. While like on the quantum computer, you have to think about how to prepare your many body wave function, and then you can sample those expectation values. So the workflow for quantum algorithms is a little bit different. So like you have an original idea, like you map that idea into the quantum language, which is like, if you're doing quantum chemistry, you're already like pretty close to the quantum language because you're treating quantum objects. It's just then that like most of the classical methods like use a lot of approximations which either don't directly work on the quantum computer or like which are not necessary, which means like you have like access to a different set of tools now. But in principle, it's like finding abstract unitary transformations which you can then chain together. In principle, then, if you want to like do some test implementation, you have to connect that with some quantum interface or quantum simulator. Like, for example, there's one by Microsoft, there's one by a Japanese group from the Fuji lab, which is called QLEX. There's one by Google, which is called Circ, one by IBM, which is called Qiskit. Once you got that to run, like more or less that your simulator spits you out an expectation value, you have to hook it up like to optimizers in order like to optimize your parameters. Get that all to work, and then you can produce some data. And this gives you feedback on your original idea, and then you can work on like improving it. And with Tequila, we aim to provide like a generalized framework like for the intermediate step, like mapping your idea to quantum operations. So like, and then automatically like translating them to simulator backends or like to real interfaces for quantum computers, giving you the opportunity to sample those expectation values and connecting it with optimizers and then run like optimizations on it. And here, that's just like a cartoonish example, like I once did. Like, let's say you have some idea in quantum chemistry, like you take one method which already exists, and then you think about, like, for example, how could I simplify those operators that they, for example, use less gates in the quantum computer, or like how could I replace them with other operators which probably have like other like properties. And here they were like just like I did like 3 modifications, which are labeled here as idea 1, 2, 3. It doesn't really matter like so much like the details of it, but like what you can then do with Tequila is like you can relatively fast have like a test implementation on it, and like first like test, does this thing actually work, and then how does it perform. And then if you do quantum chemistry, like usually you do like something like the hydrogen molecule or helium in the beginning, like just to test if your original idea plays out. But the problem with this is that usually like most algorithms just work for those systems because they're so simple, which is related to the fact that they only have 2 electrons. And then usually you want to do like, you want to go a little bit larger. Like for example, for this beryllium hydride, which gives you the advantage, like it has like 6 electrons and 14 spin orbitals. So like there are a lot of like possible combinations, and it becomes already like kind of intractable, like to do it by hand. And then you can test how does your idea like perform on this. So like, for example, if you pull the 2 hydrogens apart, which is a double dissociation, so like a breaking of 2 bonds, which is already like not so simple to describe like theoretically. So like you see, for example, in that plot, that's like the error plotted. And you see like the original already like has problems like when the bond dissociates. And here, like just for these 3 modifications, you would get the feedback like that for small distances, like your modifications, like they don't really change the behavior of your model. And then for large ones, they do. And then you can think about like, why are they doing this? And like incorporate those like realizations into further development. But it's more or less just a cartoon, like to illustrate that. With that, maybe let's dive a little bit into it. Like, how does Tequila operate, like behind the scenes?
There's actually a question on that.
Yes.
Whether Tequila lie above the compiler, or whether does it transpire for a specific hardware?
So like Tequila is like it's mainly written in Python, and like it depends on what you mean with compiler. Do you mean like the quantum compiler, which compiles like these gates, or do you mean like actual like classical compilers?
That's a good question. I think I can, I guess, follow up with him on that.
So like I can give like regarding the quantum compiler, which is more or less if you have like an abstract unitary that this is like translated into elementary gates. This is more or less, this is what's inside of Tequila already. So like, for example, in quantum chemistry, you can give all your operators if you want like an abstract language, which means like you can just provide the generators, which are abstract operators, which transform those unitaries. And then we have compilers which compile that, for example, into C knots and rotations. And then it really depends like which backend you will use. So like if you will say, okay, I want to simulate this with Qiskit from IBM, then the compiler will probably compile it into different gates than if you would say, I want to simulate this, for example, with QLEX, which is like a high performance simulator, which can also take like more abstract gates.
Yeah, so it meant quantum compiler, and is asking, in this case, for a specific set of gates and specific connectivity.
Okay, so we're currently supporting like the backends QLEX, Circ, Qiskit, and Pikewheel. And you can, so like our compiler compiles more or less like so like you give everything like in abstract data groups, and depending on which backend you will use, the compiler will compile it into a gate set which those backends like understand. And for example, if you're using the Qiskit interface and then using like a real quantum backend, then there might be the case that within Qiskit, like another compiler or transpiler is called. So like we try to translate like to those interfaces that they understand what's going on. And if they have like more sophisticated compilers which are optimized towards their hardware, then at that point, actually, they should be used.
Okay,
cool. I
cool.
hope that answers it a little bit. But we can also come back to it like later.
Cool, thank you.
Yeah, no problem. Okay, so like the general idea was a bit like, at least like in our like research group is like, we have a lot of discussions like about new ideas. And often like, this is definitely the case for quantum chemistry, but I have like the impression this is also a case like for a lot of branches of science, like currently. A lot of like new algorithms, it's like, you cannot really analyze them fully analytically. So like you cannot give the algorithm and say, okay, like for this cases, it will converge, for this cases, it will be good or bad. You can just more or less have like educated guesses. But what you really need like in the end are like good heuristics and like numerical like experiments actually like to confirm that this actually works. So like what you want is like to have like a fast way of getting like an initial toy code, like to actually just test if your initial idea, if it actually works, and like to directly like identify like potential bottlenecks, weaknesses, or like surprisingly good behavior. So like usually you have these discussions and you have like a blackboard in a room, like, and in the end you have a lot of equations like of potential ideas, but then someone has to like realize them and implement them. And this is then usually where the idea dies because it takes too long to do that and people like lose focus. So like the intent was like to provide like a software framework which makes it like relatively easily once you have like translated your idea at least abstractly in quantum language. So like what I show here in the blackboard, this is just like scribbles, but it actually does like, it's actually like a real like quantum preparation thing. It's like, you're welcome to play around with it. So like, but it's a bit like something like a Bell state preparation. And then, yeah, if you then say, for example, okay, like we can formulate our original problem into like a minimization problem of these expectation values, but we rather take the square of it, for example. Then the Tequila code, like to realize this, looks like the box below this. And the idea here is like that the top level code represents what is on the blackboard, like as close as possible, which makes like, at least the idea is like to make like initial implementation like easy, but also to make it readable for other people. So like if you see this, and for example, if you see the blackboard equations and you say, oh, maybe we should add something to that generator or to that Hamiltonian, it should be relatively easy for you like to also introduce this change in the code below. The whole thing, like how it looks on the top level, is a bit inspired by the Madness code, which is a highly developed high-performance quantum chemistry code, which is like under the hood, it's nothing like Tequila, but like the way like it presents itself at the top level is really heavily inspired by Madness. And yeah, if you're interested in that, like feel free to check it out. And then the general idea was like also that like Tequila is then able like to use at least most of the current software which is already around. So like you don't have to reinvent the wheel all the time you're trying to implement something. So like, for example, if you want to have like molecular orbitals for quantum chemistry, you can use the Psi4 or PySCF package. You can get operators like import or export them to OpenFermion. You can use different like simulations or interface backends, which are at the very bottom here. And of course, like you can hook it up to any optimizer you like. And we implemented some of them like already like in a convenience fashion that they're like easy to use with the structure, which are, for example, like all the SciPy optimizers, GPyOpt, Atom, or for example, Phoenix, which is a Bayesian optimizer also developed in our group. So like, this was also the thing, like it was often the idea came up like, we could just use Phoenix in order to optimize that problem. But then like no one like tried it out because like we didn't have code like which hooked it up before. And now it became like really easy to just do it like on a standard basis. And now a little bit like details like how the interface in Tequila looks. You're having more or less you're operating on like abstract data structures which are presented here. So like you define something like a qubit Hamiltonian, which you can, for example, get from OpenFermion, but you can also like define it abstractly, like if you already know like how it looks in terms of these Pauli operators. Then you can define abstract quantum circuits, which means you can give abstract quantum gates, augment them with controls or like multiple targets, or even like if you can also define those Hamiltonians and then just say like this Hamiltonian shall generate a unitary and this is my gate now. Those two abstract data structures you can combine to expectation values, which can then be translated to those backends by Tequila and then giving you back like the samples. And those expectation values itself can be combined to like objectives, which means like you can add them together, square them, or like transform them in any way you want. It's actually, everything is an objective in Tequila. So like also like the expectation values are more or less, it's also an objective, like it's the same data structure, it just has no transformation. And those objectives can then be combined like with the quantum backends where like all the expectation values can be evaluated and then fed into the transformation functions and then give you back the results. And the same goes on like if you want to like hook up an optimizer into that process, which means like those circuits and objectives can of course be like parameterized and then you are able like to optimize those parameters. And to give like a few examples, so like this is more or less the Tequila hello world. This is Just a simple 1 qubit expectation values. So like nothing special, like you do a usual sigma x Pauli operator as your Hamiltonian. Then you define a variable, you define like a rotation gate, which depends on this variable, but you scale it by pi. You don't have to do it. This is just like an example if you want to use those units. Then you form this expectation value, and then in principle here in this example, like you minimize like the square of it. And what it should show you like a little bit, like it's again like we tried to have this blackboard to code equivalence here. So like if you decide like to minimize the square of the expectation value, you can just square it like in code language. And this is then basically what you get. A little bit more like, for example, if you want to take gradients that works like in the same way. It's like if you take a gradient of an expectation value, which is an objective, you get back another objective. So like you can take, if you want to do the second derivative, you can just act on that objective again, because all these things are like the same abstract data class behind the scene. So like for Tequila, the system doesn't need to know if this objective you have is actually a gradient or if it's a square or whatever. It's all like the same abstract type. For everyone who's interested into chemistry, oh, yeah, I forgot about these, sorry. And then, for example, if you hit these simulate function, you can also, of course, like pass down like other instructions. So like, for example, this would be the instruction if you want to run off one of the real IBM machines. This is how it looks. If you don't pass down these instructions, like Tequila will look which of those backends you have installed, which type of job you want to have, and which backend is the best to do the job, and more or less assign it automatically. So like that's again like the black box thing. If you don't care about how these interfaces work, like you don't need to know about them. And that's like just like that's the chemistry hello world. Like you just make a molecule, you get Hamiltonians and circuits and generators from it, and then you can form more or less your approach of like or like your ideas to create those many electron wave functions on qubits. I have a little bit more details like on how those structures work in the back, and why it's like important that they all like the same abstract data structure. For example, with these objectives, so like what they are like in the end is just they hold a list of those abstract expectation values, and they also hold like a callable transformation. And this makes it like possible that you can manipulate those objectives and get other objectives back. Like, for example, you can add them, multiply them, or like square them, take the gradient, or transform them with an arbitrary function which you defined yourself. And what you get back is then just, again, like a list of abstract expectation values and like your transformation, whichever you added into that. Let's do like a simple example. Let's say you have already defined like two expectation values, like, for example, as it was shown in those two hello world snippets before. And you say you want to have an objective where you like add those two together. Then this is more or less the code which does it for you. And this is what happens in the back. So like, this is the objective that is created. Like it's a new objective which holds now two expectation values, and the transformation is just an addition. Like the transformation is just an abstract like assignment which says like, when those two expectation values are evaluated, you add them together and give me back the result. Same works for if you want to, for example, scale it by 0.5 and then square it. The objective is then you have one abstract expectation value in the list, and the transformation is just, again, like an abstract transformation here, which just tells you after this is evaluated, this is how it should be processed before it is given back. And now, since those two objectives, like they're like the same data type after the manipulation. So like you can also like take it a step further, like, for example, take the first objective and the second one and say, let's define a third one where we have the first one to the power of the second one. And here it's again like what happens in the back. What you get back is again like this abstract data structure. You have 3 expectation values in the list, and you have an abstract transformation which tells you what to do with those things once they are evaluated by the quantum backend. And this is more or less what Tequila does for you. Like, so like the top box is more or less what happens on the top level, and below is like what Tequila does with those data structures. So like in principle, you don't need to know how they look, but this is how it works. If you want to do gradients, we use like a technique called the shift rule, where you can see the paper below. And this is similar as, for example, Penny Lane does it, which is another quantum software architecture by a startup here in Toronto. And what the shift rule more or less does is like, if you have like a certain type of expectation values, it means you can, and they are parameterized, you can evaluate the gradient of it, like the analytical gradient of it, by like evaluating the expectation value twice with shifted parameters and like a prefactor, which depends a little bit on how the gate is defined. So it's a bit like taking the numerical gradient, but like it's actually like you will get the analytical gradient back, which is like a pretty cool thing. And it nowadays, like it becomes more or less like a standard tool you need to have if you work on these quantum algorithms. It's like we're doing it in the same way. If like your unitary operations do not have the properties which allow treatment by this shift rule, Tequila circumvents this by like compiling it into gate sets which allow that. One example is, for example, if you have, instead of a rotation, a controlled rotation, you can compile this controlled rotation into 2 regular rotations and a bunch of like C0 gates. And those 2 regular rotations you can then like differentiate by the shift rule. But then also like the chain rule comes into play now, because now you have like 2 gates on the same parameter. And this is more or less then what Tequila does. It compiles those things. If you demand the gradient, your circuit gets compiled into more primitive gates. And then you get back like the objectives which correspond to the shift rule expectation values. And we're using JAX for this, which is automatic differentiation software by Google. And JAX comes into play, for example, here with those transformations, because they can also depend on the parameters directly or indirectly. And then with JAX, we can compile the derivative of those transformations and give you then back the corresponding objectives when you called gradient. But it's again like the actual usage on the top level is you just say, I want to have the gradient of this objective. Like in principle, you can ignore like how it works in the back. Here's like a small toy example which like combines all of those. It's also like, it's again like it's super abstract and has like no meaning or something. It's just like constructed in order to illustrate. For example, say you have like an Hamiltonian, like it is here written in this on this blackboard. It's like X gates and Z gates like combined. Then you say, okay, like I want to do like a circuit which has like 1 gate which we call G and 1 standard C0, and our G gate is somehow generated by a Y, like a Pauli Y operator, and it's parameterized by like the exponential of minus a squared, where a is our parameter. And now we want to form an objective which is the expectation value of this Hamiltonian with respect to that unitary, plus the exponential of the square of the gradient of that expectation value. So just in order, like this is why it's a constructed example, because it's one-dimensional. I just gave it like 1 parameter. Like in principle, you can plot how it looks. And on the right-hand side, you see how this L function looks like with respect to this A parameter. And you would say, like, if you would use this, for example, for a minimization problem, this is already like not so easy. Like even if it's just one-dimensional, because it has several minima, like 2 global ones, 2 local ones. So it's probably like a nice toy example, like to play with some optimizers, or at least like to test them. And this is how the Tequila code looks for this. And I don't want to go through it like line by line, but you can also find these slides on our GitHub. And you can also find like these codes in the tutorial notebooks, which we provide there. So like, feel free to check it out there. But I hope that one can see at least a bit that the code, like again, like it resembles more or less what is written on that blackboard. And with this, you have implemented the whole problem. And here that might be like a good problem, like a good minimization problem to test actually this Phoenix optimizer, which is a Bayesian optimizer. It means like it's more or less an optimizer which assumes like no knowledge of the underlying energy surface. So like we actually now know how it looks because I plotted it down there, but like the optimizer doesn't. Like it tries to find like important points and sample more in the region of that points. And if you just run it, that's more or less the result. You see like the optimizer, it realized like pretty soon like where the important points are, like where the minimas are, and where like the unimportant points are. For example, at the border region, you see like it took like less points. Just a little bit background implementation on Phoenix, but you can check out like the original publication by Flo, which is pretty cool. The main point in this example is just like to illustrate that it's like it's fairly easy like to get up with those initial implementations using Tequila. And since my own background is in quantum chemistry, I'm always a little bit biased towards those methods. So like I show in the end like some examples like how to use it for quantum chemistry. It's again, you can find all these examples in our tutorial notebooks on the GitHub page. So like feel free to check them out. And also, if you experience any problems with it or have like questions, also like feel free to raise like issues on GitHub or like contact me directly. We're really happy like if we get any feedback for this. This is again like that's just a toy example. Say like you take a 2 orbital system. For example, I think this was it's beryllium hydride again. It's like it actually has 6 electrons and like 7 spin orbitals. But like, for example, if you want to just play around like with 2 of those orbitals and you say you want to take the B1U orbitals, this B1U is just, it's a label which labels irreducible groups of the underlying point group symmetry. If you're not familiar with this, you can just completely ignore it. It's just an abstract label for those orbitals. And you can pick them out. So like, for example, you could look what are the energies of these orbitals and just use those labels like to pick the 2 you want. And here, that's again just like an illustration of how this idea, which you see on the top of like picking those 2 B1U orbitals and then use like a specific compressed circuit in order like to solve this artificial 2 electron system and minimize it. With Tequila. You could then use this like as a first step and say like, okay, maybe you want to like try to investigate like finding an excited state of this active space of your beryllium hydride molecule. And one example is then, for example, to use something that looks like the hangman's approach to excited states, which means like, this is this little cartoon on the left. You minimize the expectation value of the ground state. Once you have done that, you define like a new objective, which is your expectation value again, but you subtract something that is proportional to the overlap with your current state with the original ground state, which just means like in principle, what you're doing is like you're projecting out the ground state of your objective in order like to assure that you're not converged to the ground state again if you minimize. And then in principle, you can play that game further, like if you want to go for higher excited states, which means, of course, also like the higher you go, the more costly it will become. But if you're, for example, just interested into the first excited state, that is still like feasible to do. You can just try it out, like Then you get like 2 potential energy surfaces. So like those are just the energies here, and on the x-axis you see again like the bond distance of beryllium hydride when you like separate the 2 hydrogens from the beryllium center atom, and then those are just the energies how the 2 states, like the ground state and the excited state, behave. This is the full code in Tequila, which produces you this plot in an active beryllium hydride subspace. And interestingly, like if you exchange the beryllium hydride here for another molecule, and again, like pick a 2 orbital subspace, the same code will also work to do it. And again, you can find it in the tutorials on GitHub. And also, like, you of course are not restricted like to use Tequila with this very small active spaces. This is more or less just like for the tutorial demonstrations that they actually run within an IPython notebook. Okay. Now, a different example here, like, let's say you want to do something, you want to combine like classical methods with quantum approaches. This is more or less how your idea for a workflow looks. It's pretty straightforward. Like you compute the CC2 method. Classically, this gives you back some amplitudes. Then you use those amplitudes and the information associated with it, like to generate a unitary CC. Like the CC stands for coupled cluster, which is a standard method in quantum chemistry. And there's a unitary version, which is frequently used for quantum computing. So like it's, again, in principle, you can use this information then to create the quantum unitary, and then you just try to minimize, again, like an expectation value, which like in a lot of cases will just be like the energy if you're interested in molecules. And let's do this. Let's say, for example, you want to do a small system, but you also want to do something like a real molecule. So like you could take the benzene molecule and just say, okay, like, but let's just look at the pi system here. So like, in principle, that means if you're not familiar with the terms, the benzene molecule has a lot of like electrons and orbitals, but like there's this ring system, which is also in the chemical cartoon here. And you take more or less only the orbitals from this ring system. This is the so-called pi system. They are 6 spatial orbitals, so it means 12 spin orbitals, and you can fill them with 6 electrons. And here it's now just an example like how you could solve like this workflow here with the benzene pi system. So like first you compute your Hartree-Fock, or like which is the mean field method, which defines your original orbitals. We use here the psi4 backend. You see again, like it's never specified that psi4 is used, because that's again like it's more or less picked automatically depending on what you have installed. You give the name of a file which has the molecular geometry of the benzene. You define a basis set, and again like an active space. This active space here, it's again like these symmetry labels, but they just pick those 6 pi orbitals you have on the lower right. Then we create the qubit Hamiltonian, which is then pretty easy. Like once you can in principle define also the encodings, like for example, Bravi-Kitaev or Jordan-Wigner. If you don't define the encoding in your molecule, like Jordan-Wigner is currently the default, then you can compute the CC2 amplitudes, which is again, it just uses psi4 and gets like the information from it. And then you use those amplitudes in order like to define an ordering, and then define a trotterized version of unitary coupled cluster. For example, you can also, of course, like start exploring and do like your own unitaries. And then you can minimize it, also like maybe compute some classical energies with the psi4 interface, and then start, for example, comparing the BFGS optimizer with a gradient-free Kobyla optimizer. Maybe you can even use Phoenix. So like those are just examples, but in principle, so like at this point you can start playing around like with your original idea and see like how it performs. And yeah, we're currently using it in the group for ideas in quantum chemistry and quantum optics. And this was more or less like the idea behind it. And also like one of the ideas is then, of course, that like we can, once we have, for example, a new method, we can provide the code within Tequila, which makes it like easily accessible and extendable for others. And we hope at least that maybe some other people will also use it for that. And you're, of course, free to do so. It's open, like, to contribute. You can go to GitHub, fork it, make pull requests, ask questions. Feel free to do so. Like, we're really happy for feedback. With that, we come to the end. This is here I show you like the people which are mainly involved in that project. It's of course like Alan, which is the head of our research group. Then we have to mention Samna Alper and Leah, which is a grad student here, who does like a lot of work in Tequila, and he's like from the grad students, like the one which mostly involved like with developing this software. Then we also have Teresa, Cyril, Abhinav, and Alba, who helped a lot with the initial implementation and are still currently like working on improving the code base. You have below like the picture of the whole group, and on the left further people which helped with certain aspects of Tequila, or who are currently like implementing some features for it. I want to mention like Thompson Yen and Vladislav from the Ismailov group. They did, for example, this optimized measurement scheme, which I briefly mentioned in the beginning, which is available in Tequila already. It's currently not on the public version, but it will be there like in the next weeks. With that, I come to an end, and I'm happy to answer any more questions if you have some.
Cool. There are 3 questions actually that showed up over the past few minutes, so I decided to let them roll into your flow. So you can take a look at them, or you want me to read them for you, in case you need to reference the slides.
Oh yeah, sure. Okay, cool. So like the first question, yeah, that's actually a very good question with the shift rule. So like the question is, the shift rule, like, it applies only to specific classes of gates. So like I think in a nutshell, it's like if the generator of this gates only have like 2 distinguished eigenvalues, then you can apply the shift rule. But for others, you cannot. Like, for example, you can do it for a rotation, but you cannot do it for a controlled rotation. This is taken into account in Tequila. I can go back to the slide because I probably rushed over it. Just Bombardier, can you still see my slides?
Yeah, I can see your slides.
Okay, great. So like if you define like a circuit, for example, you do a circuit and you do a controlled rotation in it, and you have it parameterized, and then you call the gradient on Tequila. What Tequila will do is like it will take this controlled rotation, compile it into 2 regular rotations and a bunch of C-naughts, and then use the chain rule combined with the shift rule, and potentially jacks if like your parameter itself is like also transformed. Like, for example, in one of those examples we had that the parameter was actually like the exponential of the actual parameter. And all those things are like combined to give you back the gradient. And currently, like for all gates accessible within Tequila, that works. If you do something like, if you would currently hack it open a bit like and define your own gates over matrices, you might get into trouble. But like in principle, it also works like by doing a trotterization, but then the gradients become like pretty expensive. So like in a nutshell, like Tequila does this, like it uses, like it compiles to more primitive gates and gives you back the gradient, but it doesn't mean that your gradient is like necessarily cheap. But this can also be then like, yeah, part of research that you realize this, that like for your idea, like gradients are pretty expensive. One example is, for example, if you have, let's say you have a multi-controlled NOT gate, and you have you parameterize this with an exponent. then especially if you have like a lot of controls on it, the compiling becomes pretty intense. Like you get a lot of gates back, but in principle it works. I hope that answers the question. So at least this is how I understood it. Feel free like to correct me on the chat or over microphone or however you want.
Thank you.
Oh, with the largest basis set implemented, there's no limit. It's currently like, for example, the main module you use for quantum chemistry and which works the best currently is Psi4. So like the largest basis set you can use is the largest basis set that Psi4 can use, which is usually, I think they all stop beyond I orbitals. So like you have S, P, D, F, G, H, I. And if you would do like a K orbital, usually Psi4 will say you that it is not able to do that. But I think that would be actually so large that that like qubit-wise, that would be like a gigantic system. But in principle, you can use whatever you want. So like maybe to put it in another way, if you use this molecule interface of Tequila, the basis set you can give any name that Psi4 understands. You can also give your own name if you provide a file which has like the basis set information which lies in the same directory. So like, yeah, in principle, there are no limits. In practice, there are, because like pretty soon you have a lot of qubits and will not be able like to simulate them. That's also like a nice question with templated VQE methods. I think that is more or less like, it's like I at least would hope so, like that, for example, if someone does like a new VQE method, that those templates are provided. I currently have some of them, which is, for example, this unitary pair coupled cluster, which was developed by the Head Gordon group. That's not yet in the public repository, but sooner or later it will be there. For those, it's actually like the template of this. It's like, it's again like, it's since like the API is since we tried like to make the API pretty simple. The template for this are actually just like 20 lines of code. Then for quantum subspace expansion, like I surely hope that that we have something like this too. And I'm currently trying to convince like some students like to do like at least some tutorials on like how to do that, because like in principle we have the technique to make it. But this is also like it's an open source software, and of course like everyone is like free to provide templates or modules or classes for their favorite method.
Cool. Thank you. That's the only questions we have so far. I have one for you. How was it? You mentioned some of the packages like OpenFermion and the others. How hard was it for you to integrate them with the Tequila? Did you get some kind of input from them? How helpful were they?
I think the hardest was actually Psi4. Psi4 and QLEX were the hardest, but the others, so like everything that was already like fully defined in Python is like pretty straightforward to integrate. QLEX was a little bit hard because like when we started with it, like it had like the documentation was still in Japanese. It got a lot better now actually, but it was still like fairly straightforward, like to figure out how it works. And Psi4 was a bit more challenging, but this was actually just because like this is like a really advanced quantum chemistry package which can do like a lot of methods, which means like you automatically have like a lot of different keywords can like clash or lead to unsuspected behavior, which is like quite normal there. So like we learned a lot about the usage of it, and it now works fairly well. But for the others, I would say it's pretty straightforward actually.
Cool. Someone is asking about your slides on the chat. how did you make these nice chalk blackboard?
It's funny because Alan asked the same thing when he first saw it. I used the Inkscape. It's like a free vector graphics tool. And I have to say, like, I'm not so good with those things. But it was fairly easy to do it there. So like it has the entry curve is not so steep. And then for the you can just download some chalkboard font or something for the letters.
I assume at the end of the day, you can share some of the references, including these tools. I can email everybody. They can have the link. There is a question on the Q&A section.
Oh yeah, I have to open it. Oh, it's on top here.
Yep. Yeah, I can also read it if.
Okay. It was okay. Which one is the new one?
It should be the one that says top one. There's only one. All the others have been answered.
Oh yeah. Sorry, like I had the wrong tab open. I didn't saw it. Okay. Sorry, it's the first time I used this tool here. That's a pretty good question. So like, I think with the current NISC hardware, it's pretty tough to beat the classical algorithms, especially in quantum chemistry, because they're like super advanced. For me, like the main advantage of this quantum algorithms is that they provide like a different framework where you can try different things, which might become useful like once you have powerful machines. But like outperforming will be hard actually. But I think if the hardware gets like, if you have something like 100 qubits, which works more or less robust, it's like not necessarily full error corrected, I think you might be at a point where you can actually do like some cool computations. You can then still probably not like, you could like still do something like quantum Monte Carlo classically and just like brute force solve the problem. But like once you're at that point, it's like you're beyond if you're doing like experiments on 4 qubits or 2 or something, it's usually like that the problems you're encoding are too simple. It's like, for example, this hydrogen molecule, in my opinion, like it does not reflect like a lot of the problems you have in actual quantum chemistry. It's like you can't go beyond the proof of principle thing. But once you have like something as 100 qubits, you might not necessarily be better classically, but you can at least like more accurately like test your algorithms if they are actually able to solve real life instances. Because like if you're able to solve molecules encoded into 100 qubits, you probably also are able to solve it into 200 qubits when the hardware is available. While like if you're able to solve something on 2 qubits, it doesn't necessarily mean you can solve the similar thing on 4 and 8 qubits, because like then you just have so much more like configurations in your molecule. But it's tough like to estimate it. Like I just like the framework, like that you can like develop new ideas, which might even like lead back to like new classical algorithms. You never know.
Cool, thank you. Taking on that question. I guess a final one from me is next for Tequila. Do you have any major releases that the audience should be looking at for?
I mean, like, yeah, we're currently, you could call it like an open beta, like it's on GitHub and free to use. We try to do like a cloud release like soon, that you have like an official version, more or less. We have like some papers coming out in quantum optics which actually use it, which might be like useful like for like different kinds of example, like how it was applied, which I didn't show here. And we have some quantum chemistry projects, but they're like still in the pipeline. So like I can't tell too much about it, but like I guess they will also come out like at least like hopefully in a few months. But let's see.
Cool. Thank you. So I think there are no more questions. So thank you so much, Jakob, for taking your time. It was a great insight, really. Open source is really enabling the development of these fields faster than before. And there is a really great opportunity for people to jump in with tools like Tequila that kind of minimizes the barrier to entry from having ideas to trying to implement them. So yeah, thank you so much for sharing about the tool. To everyone, this is our last webinar for this month. I will send you an update once we have the confirmation from Dr. Chancellor about his talk. So for the time being, thank you so much again, Jakob. Big round of applause for Jakob, and see you in the next webinar. Okay.